So now, yeah.
I think this assumption is very general. So can you give us an example of that, a counterexample of this assumption?
Sure. If x1 and x2 are correlated, you can't model that using this. Like, for example, in the spam case, let's say the words Nigerian and the word prince are very correlated with each other, right? This model says, well, I don't model that correlation. Like, if I were to draw a sample, subject header email, conditioned on the email being spam, the probability of there being Nigerian in the email header is independent of the probability of there being prince, even if both are high, right? But in reality, we know that they're correlated. Right? So it's a simplifying assumption. Yeah.
Aren't there good examples where that is indeed a good assumption, a decent assumption?
You know, in the modern world of like deep learning and like heavy-duty logistic regression, decision trees, crazy decision tree ensembles, the naive Bayes assumption is a pretty poor assumption when you're trying to maximize prediction accuracy. I think it's still a useful model to think about because it's the simplest probabilistic model, and if you're interested in probabilistic models, there are many useful probabilistic models. But in order to become comfortable thinking about probabilistic models, you have to start with naive Bayes. Right. Maybe that's the right way to answer it. And naive Bayes is still useful. There are still many prediction tasks that are simple enough where it works fine. And SVM will probably do a little bit better. But SVM, as you'll see really quickly, this actually requires almost zero computation time in terms of training. You just measure counts, right? Histogram counts. Whereas in SVM, you have to solve an optimization problem. Now again, nowadays that matters a little bit less than it used to because all the optimization techniques are so advanced. But it used to matter more back in the day. I guess I'm being a little bit apologetic about naive Bayes. But I think it's a very useful concept to really master because it's the stepping stone for more advanced probabilistic models. Yeah?
If people go in, it seems like you could just look at correlations in the data and say which features seem to actually be correlated with those don't. So can you make mixed models where you know?
Yeah, so you could do a naive Bayes version where you model instead of individual x's, you model all pairs of x's. So now instead of linear in D, you have a model complexity that's quadratic in D. So you can do that. Yeah. But then you're not modeling trigrams, right? You're modeling triplets of words, and at some point you get to the full exponent. Like at some point you're unstructured.
Yeah. It just seems like there'd be, I guess, there's be some sweet spot in there for a given problem.
Yeah, many people do offer bigrams. Yeah. Okay, so why is naive Bayes convenient? Well, it has a very compact representation. The number of parameters scales linearly with the length of the feature vector x. As I'll show, it's easy to compute any quantity. It's easy to estimate the components, easy to sample, easy to deal with missing values. So here's an example of a model. I just instantiated it. So this is the P of x. So remember, this is the structure of the model. It posits a P of y, and then it posits a P of x given y. And this specifies the joint model, which is with some structural assumptions. And so here's the matrix of P of x given y, and then here's the P of y. Right? So according to this model that we already have, or that were given to us, or we trained from data, the prior probability in our training set, or this distribution of an email being spammed is 70%, not being spammed 30%. Condition on the email being spammed, the probability that the word homework appears in the subject header is 20%, and the word winner appears in the subject header is 50%. Condition on the email not being spammed, the probability that the word homework appears in the subject header is 60%. The probability that the word winner appears in the subject header is 10%. And the negation of this is just 1 minus the values. Right. So model complexity is linear in the length of x. That's the key sort of representational advantage in terms of compactness. Okay, making predictions. So this is sort of the classical prediction task, where given an input feature, we want to predict the probability of the label, and then if you really want to pick a single label, you would take the y that maximizes the probability. According to the law of conditional probabilities, do this. This is just these two steps combined gives you Bayes' rule, and then this guy factorizes by the naive Bayes assumption into this. And then I'm just going to ignore the p of x and just say this is proportional to this. Right? And keep in mind that these are the components of the model that we keep track of explicitly in our model representation. Right? Okay, so now just a very concrete example. Right? Suppose in our model that these are the values that we estimated. Then if we want to estimate the value of for some x, right? Then if we want to compute the probability of y equals 1 given x, it is equal to this guy times this guy divided by this guy plus this guy plus this guy. So as you recall, in this equation we show that it's proportional, and because it's proportional, to compute the probability, we just normalize by the sum of all possibilities. But the sum of all possibilities is just the sum of all possibilities of y, and there's only 2 possibilities. So normalization is easy. That's why I can throw away the p of x, because I can renormalize very easily. So even though the prior probability of y being positive in the positive class is only 30%, because the evidence is so much stronger, because of the x that we observed, it's so much more likely to be generated by a positive y than a negative y. Given that we observed this x, the probability that we're in the positive class is now 96%. Was that a question? So example number 2. So what if we want to compute this probability, right? So this is maybe not an unorthodox one, but if we could reimagine that x, the first feature is somehow the label we want to predict instead. This is the probability we want to compute, right? It's actually very simple. You just look up an entry in the table, right? Each p of x is conditionally independent given y. So this thing is equal to this thing. We can just throw away this because x1 does not depend on the other x's if you're already also conditioning on y. And this is simply an entry in the probability tables that we already keep track of. So it's a simple lookup.
So you're saying here we're using the naive Bayes assumption, is that the...
Oh yeah, all these examples are naive Bayes, yeah.
Okay.
Yeah.
So otherwise it wouldn't be true at all.
That is correct. Okay, here's example number 3. Suppose we want to compute x1 given the other x's, but we don't actually condition on y. We don't know what the y is. We didn't measure the y, or we threw it out. Right. Well, the way you would compute this is you would just simply marginalize out the y's. But we compute sort of what would this probability be if y was the positive class? What would this probability be if y was the negative class? Take the weighted average of those based on the relative frequencies or likelihoods of the y being the positive negative class, and then that's our answer. And that's what this formula basically represents. Now the numerator is smaller than the denominator because recall that this thing is so here x is all of x. Here x is just all the x except for the first feature. And since this is a product, this thing is a product, this thing is multiplying more things than this one, and all these numbers are less than 1, therefore the numerator is smaller than the denominator, in case that is a point of confusion. Something that's very convenient is to represent everything in matrix form. You can, for large models, you can, and even when you do like stochastic gradient descent and do matrix sort of derivatives, you can write everything in sort of terms of for loops, and that'll run. But most modern machine learning platforms like NumPy and stuff, and in MATLAB operate much faster if you do a matrix operation. If you represent your for loops as a matrix operation or a vector operation, right? Suppose we want to compute, suppose this is our matrix, I'll just call this O, and this matrix is called P, just for the slide. And suppose we want to compute the probability that the first feature is 1, irrespective of what the other values are, just marginalizing over all the other variables. Well, that's equivalent to this. Actually, sorry, in this example, it's equivalent to this. And that is simply, you take this matrix, you transpose with this matrix, you look at the D row, or in this case, the first row, right? Or the second row. And if this was a big matrix table, this matrix operation is going to be a lot faster than running a for loop. This is not actually relevant to the data sets and the models we deal with in class are small enough such that this is not going to be any major bottleneck. But if you actually are interested in thinking about how these things really scale to large models, this is an important concept to understand. And it's also sort of how mathematically convenient, right? If I write this, like in like Python or MATLAB, you know, debugging is a lot easier than like looking at a block of nested for loops and trying to figure out what's going on. Right? So once you become comfortable thinking in terms of matrix and vector notation, the code just gets a lot more compact, and you actually can read it much more naturally once you get comfortable in thinking about things in matrix and vector notation. Okay, dealing with missing values. So suppose we want to predict the probability that so we have two features: whether the subject contains the word homework or whether the subject contains the word winner. And suppose we don't, for whatever reason, the data was corrupted. We didn't measure whether or not this email subject contained the word winner. But we still want to predict the probability that the email is spam, conditioned just on observing the first variable, whether or not the subject header contains the word homework. How do you do that? Well, you just write. We have the joint probability, so we just write this out. Use the law of marginal probabilities, and then use the law of conditional probabilities and get something like this. Right? What does this mean? This means, and in this case, since d equals 2, we're just summing over one variable, all the possible states over one variable. But in general, it could be multiple variables. What does this mean? It just says, I'm going to look at all possible values that the second feature value can take. In this case, two values, one or 0. And I'm going to compute this ratio and sum it up. And that, using just the various probability identities, will give you this. And why does this work? Because we have a joint distribution over x and y, so we know from the training data how frequently x2 happens. It's a little bit more complicated than that, but that's the basic idea. One thing that you might wonder is, okay, suppose we had more than just suppose we had more than just two missing values, right? Suppose we had 10 missing values. It seems like this summation over all possible instantiations of 10 variables is going to be exponential in 10, right? 2 to the 10 possibilities. Right? So is this efficient when I have a large number of missing values? And the answer is yes for naive Bayes. And conditional independence, the conditional independence assumption is why this is true. So this is from the previous slide. It's the definition of naive Bayes. I'm going to write, I'm going to just factor out this term because it doesn't matter, it's constant within the summation. I'm just going to take a look at this term, write it out according to just replacing with the definition. Right? And it turns out, because of independence, I can just swap the sum and the product. And I'll give you an example in the next slide. But it turns out I can just swap the sum and the product. Now, suddenly, instead of doing an exponential number of iterations, it's back to linear. So I'll give you an example in the next slide that's operational. So let's consider the case of 3 variables. And so I just wrote out this in 3 variables. So this is the joint distribution, summed over the second and third variables, definition of naive Bayes. I'm going to show you that it equals this. So we can write out this part as basically, this product is a product over 2 variables, the second and the third variable. Right? And then this sums over all possible combinations of the second and third variable. Right? So this is just that equation. And why did I write that? Okay, I don't even know why I wrote this. I will correct that. But this is the main point. So if I just expand this out, then it's just probability of x2 equals 0 times probability of x3 equals 0 plus probability of x2 equals 1, probability of x3 equals 1, plus probability of x2 equals 1 times probability of x3 equals 0, and so on and so forth. There's four possibilities. By the distributive rule, I could rewrite it like this, right? Just by the distributive rule, probability of x2 equals 0 plus the probability of x2 equals 1, so on and so forth. Oh my god. I don't even know if you open my laptop. Okay. So comparison with logistic regression. So naive Bayes can query any distribution from the joint distribution. Training just requires counting. But it's not optimized for classification accuracy because it's trying to fit the joint distribution. Logistic regression can only query the conditional distribution of a specific pre-specified y. Training requires an optimization procedure because you need to do gradient descent. There's no closed form solution. And it's trained to directly minimize the log loss of the prediction task that you care about. Someone asked, how well does naive Bayes do in practice? And here's a relatively recent comparison of a few different methods: boosted decision trees, random forests, and these are various columns. That's like sort of first, how often the model gets first place, second place on a range of tasks, and 10th place in terms of accuracy. And as you can see, naive Bayes places dead last, very frequently. There are data sets where it does a little bit more competitive than that, but you know, it is not a very competitive model compared to like a very powerful model class like boosted decision trees or random forests. Right? So if you already know the y that you care about, you know that you have no missing values, and you know you don't care about any of that stuff, you should probably not use naive Bayes. How do we train a naive Bayes classifier? Well, maximum likelihood over the training set. Subject to the naive Bayes assumption on the structure of this structure. And I won't go through the derivations. It's basically the same as before, but once you impose the structural assumptions, it's just simply the frequency count again. So the probability of y equals spam is simply the number of times in your training set that a document or an email is labeled as spam divided by the total number of documents in the training set. The probability that the first feature appears in the word of course on the first feature appears in this subject header of this document, conditioned on the document being labeled as spam, is simply the count of how often both criteria happens in the training set divided by the number of documents that are labeled as spam. And once you compute these two for both, you fully specify the naive, for all possible sort of combinations, you fully specify the naive Bayes model. Regularization works the same way as the previous unstructured model class. You just add pseudo counts. It's the most standard way to do regularization for naive Bayes. And it's basically the same way. And often you just set pseudo counts to uniform distribution. So P here, P y equals spam would just be 1/2. And lambda is the number of data points you hallucinate. Lambda doesn't actually need to be an integer. You could hallucinate half a data point. Like somehow, if you think that you only need to hallucinate half a data point for very little regularization, that's also fine. Sampling. So naive Bayes is a generative model, so it defines a full distribution over x, y, which means if you have trained a model of naive Bayes, you can treat it like it's the test distribution. It's a model of the test distribution, so you can actually draw samples from it. Right? So naive Bayes model, remember, looks like this. How do we draw samples from it? Well, you can do the following. First, you sample the y, right? Which means you draw a uniform random variable using some built-in function. And then since y has two possibilities, you set y as spam if the random variable is less than the probability mass of this guy, and otherwise you set y as not spam. And then condition on having sampled y, right? This actually specifies a sampling procedure as well. How do you specify a sampling procedure? So condition on having sampled y, we now sample p of x given y. And now each p of x given y is conditionally dependent given y. So for each dimension, we sample again a new uniform random variable, and then we set that feature as active if the probability of that feature being active according to the model condition on the y contains this random variable, otherwise 0. There's a few examples. Let's sample random variable. The random variable is 0.5. So we're going to say set y to spam. Sample another, it's going to sample x1. Given y equals spam, we sample a new random variable equals 0.1. Y equals spam, x1. So it's less than 0.2, so we set x1 equal to 1. And that should be x2. I apologize, I fixed that. So for the second feature, give conditional y equals spam, we sample random variable 0.9. And it's above this probability mass, so we set x2 to equal 0. And because these are independent, they can be done in either order. Doesn't matter. And in fact, for large-scale probabilistic models that have these conditional dependence assumptions, you often sample these in parallel on multiple cores simultaneously. Just draw another sample from this distribution, right? We'll draw a random variable for sample p of y. Random variable 0.9. So we're going to say y equals to not spam. Condition on that sampled y, we sample the first feature. We'll draw a random variable, 0.5. So not spam. So it's less than 0.6, so we set it to 1. For the second variable, condition on y equals not spam, we draw a random variable, this time just uniformly randomly. It's a small variable. And so it's less than 0.1, so we set the second feature to 1. And so you could just do this many times, and draw samples from this distribution, and see if it mimics the distribution of your training set. So it's a simplified model of the test distribution, essentially. Like when you model a joint distribution, you model with the test distribution. Okay, just to recap on naive Bayes. It's a probabilistic generative model. Makes very strong independence assumptions, but that leads to a compact representation, easy to train, easy to prove various probabilities, not the most accurate for standard prediction tasks. You could invent your own model, right? I just gave you one model. Suppose for whatever reason, I just made this one up, right? Suppose there's two y's that I care about, right? And I believe that the x's were sampled, the generated distribution looks like this, right? Then just given this graphical model representation, I can specify the independence structure of this distribution, right? P of the joint distribution, y1 depends only on y2, y2 depends on nothing, x depends on both y's, and then if I further refine this p of x given y, the last variable depends on both, and then the first d minus 1 only depends on y1. So now I've written out the distribution. Now, if you want to make other assumptions, like maybe this has a linear form or something like that, you can do that. But this graphical model representation gives you the independence assumptions. And if you take the naive Bayes sort of, if you take the minimal assumptions, if you take minimal assumptions given these assumptions, then what you do is you compute probability tables for each of these quantities, right? And that's what I did for the naive Bayes example. Okay, so I'm going to spend a few minutes overviewing a few other probabilistic models, just so you get a flavor of some of the other probabilistic models people use or have used in the past. I won't go into details. The derivations are based off the same principles as before, but they may require more math because, for example, if you make a Gaussian assumption, you have to do the Gaussian updates, like Gaussian naive Bayes. So it has the same independent structure as naive Bayes, let's say y is binary, so p of y is the same. But let's suppose each feature is a continuous variable instead of discrete, right? So this is, and so because it's continuous, you can't really model it as a probability table, right? And so one assumption is to say, well, suppose that the distribution of x of d, given whatever, is some normal distribution, right? Gaussian distribution. Then the model estimating this parameter is simply estimating the mean, right? There's no probability table here. It's just the number of parameters here is just the mean. I can also estimate the variance, or I guess this should be sigma squared, right? I can also estimate the variance if you want, or I could just pre-assume what the variance is. And so now, the maximum likelihood estimate of a Gaussian naive Bayes is the p of y is the same, it's just the histogram counts because the y is binary, and the x's is just you just compute the mean. And it's just a single number. Hidden Markov models, which we'll talk about a lot in the next lecture, because it's the major part of the homework, is a generative model over sequences. So at the very beginning of this course, someone asked about, if you had video and frame by frame, the videos are not independent of each other, how do you actually model that in an IID way? And I answered, well, you can model the entire video as a single input instance, but that leads to a sequence modeling problem, right? Instead of binary classification, now we're classifying sequences. And so hidden Markov models is one way to model an entire sequence. And so hidden Markov model is very similar in sort of the underlying independence assumptions as naive Bayes. You have a sequence of x's, and then you have a sequence of y's. So the canonical motivating sort of example is part of speech tagging, where x's are words, a sequence of words in a sentence, and the y's are part of speech tags, like determinate noun, verb determinate noun. And I'll go into more details in the next lecture. And the idea is I want to model the joint distribution of sequences of words and sequences of part of speech tags. Because some words, like rain, is both a verb and a noun. So given some sentence where rain appears somewhere in that sentence, can I model the probability that the rain in this sentence corresponds to a verb or a noun, given the surrounding context of the sequence, right? Similarly, you could imagine all these examples if there's ambiguities. And so what the hidden Markov model assumption is it's an independence assumption. Again, you could read off the independence assumption by just the arrows. So there's joint distribution, and the joint distribution, so the y1 doesn't depend on anything else, and then the x1 only depends on y1, and then y2 depends on y1, y2 only depends on y1, so this product encapsulates this part, where the yj depends on yj minus 1, and then the xj depends on yj. Right? Why is this representation compact? Well, because this table is replicated for every frame in this, for every time step in this sequence. It's the exact same probability table, just replicated. So that's why it's compact. And again, I'll get into more details in the next lecture. Question?
How do you generally know if the structure is present in the system? How do you...
Like this specific structure?
Yeah, exactly. How do you know that?
Right, so this structure, this is a very strong independence assumption, right? It's basically saying, for part of speech tagging, the probability of this word having this part of speech tag depends only on what the previous part of speech tag was and the word. So for example, if it's the rain, right? Then if I estimate that the part of speech tag is most likely determiner, because the is usually a determiner, and then rain is either a verb or a noun, but I know from my determiner part of speech tag transition matrix that what follows a determiner is usually a noun and not a verb. And that's how I can infer that it's more likely that it's the rain, then rain more likely corresponds to noun rather than verb. And there are many cases where just a simple look back one word assumption, which is what this independent assumption enforces, is the wrong assumption, or a highly suboptimal assumption. There are many cases where you're going to look back 2 words, let's say, right?
Because given the case, you basically decide if it's reasonable to take this as an inconvenience assumption.
I'm sorry, you said given the...
So you're given the case, and you basically decide just like, oh, that makes sense. And then you go, there's not like a way of like, I don't know, verifying that.
I see,
that
I see,
matches
I see, I
with
see. You can test, okay, let me see.
I guess is there like a way of like, oh, I can follow this procedure and then I can verify hidden marking model is the thing that I want to estimate. What's the difference with graphical model?
Right. So yes, you could be even more meta, right? You could posit a distribution over structural assumptions, right? Now it's a nested generative model. I posit a distribution over structural assumptions, and then I see how well they fit the data, and then I use the one that is that fits the data the best. Of course, the more complicated your model, the better it's going to fit the training data. So you have to add a regularization penalty saying that a priori, it's far less likely that I would want to use a second order hidden Markup model where I look back two time steps and depend on both y-1 and y-2 than a first order one. Unless I have an overwhelming amount of evidence that's what I want.
So you can run like model selection techniques over there.
That's basically Bayesian model selection. Now, if you do Bayesian model selection, now you have to specify how much evidence, like the Bayesian model selection part requires you to specify a prior. Like how much evidence do I need before I'm willing to use a second order hidden Markup model rather than a first order hidden Markup model. And again, that's something you have to handcraft as well. Because if you don't penalize, you're just going to fit the training data perfectly with a nth order hidden Markup model, which is unstructured. Right? Okay, another class of generative models are called mixture models. What mixture models says is, okay, we have a bunch of data points, and each data point can be generated from one of k distributions. I don't know which one. So this is, you can think of this as the probabilistic analog to clustering. So the basic idea is you have n data points, denoted by x sub I. Each data point corresponds to another variable z sub I, which is a membership to one of k distributions. In this case, k Gaussian distributions. So for example, for the one-dimensional case, if each x is one-dimensional, then in my training set, I might observe data points that fall along this distribution. So for this value of x, I observe this much data. For this value of x, I observe this much data. And then if I posit that this data was generated by a mixture of 3 Gaussians, then this would be the 3 Gaussians. And every data point is a mixture of one of these 3 generated by one of these 3. So how the generating process would work is, for every data point, if this is my representation of the test distribution, for every data point, when I sample, I first sample a Gaussian, one of these 3 Gaussians. I just pick a membership ID, that's the z, and then I sample a point from this Gaussian, and then that's the point, right? So if I only sample from the first Gaussian, then my data's test distribution is going to look like this. If I only sample from the second Gaussian, my test distribution is going to look like this. If I only sample from the third Gaussian, my test distribution looks like this. If I have a first step process where I sample the Gaussian membership ID and then sample from that Gaussian, then my test distribution is going to look like this.